Okay, so first we start with discriminant analysis. So discriminant, the word itself, conveys the meaning of this. So discriminate, discrimination, right? So from that word, this analysis also, they have given this name, discriminant analysis. So a little bit of theory, we'll see what is that and what we can do with the discriminant analysis, and then we'll see how to do it with the help of dataset in SPSS. So discriminant analysis is a multivariate statistical technique. So we have univariate techniques, we have bivariate techniques. So this comes under multivariate techniques. Say we have a multiple regression, we have MANOVA, we have discriminant analysis, cluster analysis. So all these things comes under multivariate statistical techniques. So that is for predicting the probability that an object will belong in one of the two or more mutually exclusive categories. So the dependent variable generally in discriminant analysis is categorical in nature, and the independent variables are scale variables. So in a regression analysis, if you recollect, in a regression analysis, both the dependent variable and the independent variable would be a scale variable, and we'll have a set of predictor variables called independent variables, and there'll be a dependent variable, and we'll try to assess how far this independent variable can explain the changes in the dependent variable. So same concept, but here the only difference is the dependent variable would be of a categorical in nature. So it will be a nominal variable. In SPSS, the data type, it will be shown as nominal. So it will be nominal variable, and independent variable should be a scale variable, to be precise, on a ratio scale or an interval scale. So this analysis has got wide application. So I've given some examples from business perspective. A HR manager might want to differentiate or distinguish between applicants to be hired and rejected. So a HR manager who receives applications from quite a bit of number of applicants, and out of which on basis of a certain criteria, he has to decide, or he has to differentiate a application to be hired and the application to be rejected. So that is one example. So here there are only two options: hire or rejected. So this will be the dependent variable, and there could be a set of predictor variables or independent variables which would predict or which would decide whether to be hired or rejected. Same as that, a bank manager might want to discriminate between the probable defaulters and non-defaulters. So banks, they give loans to customers. So they wanted to predict which are the customers might default and which are the customers might not default based on a set of identified independent variables. So here the dependent variable has got two categories: defaulters and non-defaulters. So in these kind of situations, the discriminant analysis could be used. Discriminant analysis types, depending on the number of categories the dependent variable is possessing. So in the previous example, I told you hired or rejected. Second thing I told, defaulters and non-defaulters. We had only two categories under the dependent variable. So depending on that number of categories in the dependent variable, the discriminant analysis could be classified into two types. Either it could be called as a two-group discriminant analysis, or it could be called as a multi-group discriminant analysis. It might look similar to a logistics regression, but there's a slight difference. Discriminant analysis could be used when we have a normal distribution, whereas the logistic regression could be used if in case data is not normally distributed. And logistic regression is only binary, yes or no kind of a situation. Here we can have multiple categories in the dependent variable. Objectives of discriminant analysis, I have listed some 5 objectives. So first is, when we run the discriminant analysis through SPSS software or any software, one of the main objective is to determine the discriminant function. So we have to write the discriminant function, or it's a linear combination of the independent variables, which will best discriminate between the categories of the dependent variable. So in the example I told you, applicant to be hired or rejected. So we have two categories. So a mathematical function that would clearly distinguish or differentiate or discriminate between these two categories, whether he has to be grouped under hired category, or that applicant has to be grouped under rejected category. So that function has to clearly discriminate. So that function we need to arrive at. We have to find that function. Second objective, examination of the significant difference among the groups. So we have two categories. So these two categories should be the opposite ends. So there should be significant difference between these two groups. They should not be close to each other. The two categories should be well distant apart. Determination of the independent variable that contributes the most for the intergroup discrimination. So in your model, you could have 4 or 5 independent variables. So out of the 4 or 5 independent variables, which variable contributes the most for that discrimination? So that has to be computed or determined. So that is the third objective. Fourth objective is classification of the cases to one of the groups based on the values of the independent variable. So we have the set of independent variable with which we are trying to predict. With that, we need to classify that particular case, whether it should be classified into group 1 or classified into group 2. In our example, whether we have to classify it into hired list or we have to classify it into rejected list. So that we need to classify it. So first we create the model. Second, we examine the difference, whether the difference is significant statistically between the groups. Then we determine the independent variable that contributes the most for the discrimination. Fourth, we need to classify the cases individually, and we need to group them, or we need to classify them into group 1 or group 2, or if you have more groups, we have to classify into the respective groups. Evaluation of the last objective is we need to evaluate to what extent the classification has been accurately conducted. So only then we can validate the model, so that we could use the model which we have developed for the future predictive function or classification function. So discriminant analysis is primarily a classification algorithm, which we could use it. So with the known data, we could find the classification, the discriminant function. And then with that model, what we have arrived at, we could apply to a new case or new data set, and we can classify them based on this function what we have derived out of our analysis. So the discriminant model would look like this. It would look similar to our regression model. So here the discriminant function or discriminant score is mentioned as D. In some of the books or websites, they might have also used Y. So here, in regression, we use the variable Y. So D has been used here for discriminant score. So D is equal to B0 plus B1 x1 plus B2 x2 plus B3 x3 plus etc. up to Bn xn. Same as the similar to the multiple regression model, where we used to say Y is equal to constant plus m1 x1 plus m2 x2 plus m3 x3. So same as that here, D is equal to B0 plus B1 x1. So the B's, all the B's are called the discriminant coefficient, or sometimes they are referred to as weights, are the multiplication factors, and the X are the independent variables. So it could be anything. Say, for example, if the bank example, if you take, if it is based on their bank account balance, the example what I gave was a bank manager wants to predict a list of customers, and he wanted to classify them into probable defaulters and non-defaulters. So the way independent variables could be their bank balances, their healthy transactions, is there any check bounces recently, whether the previous loan has been bounced or not. So like that, they will have a set of independent variables with which they can predict whether in the near future the customer is going to default or not. So like that, these independent variables are mentioned as X over here. So we'll just open that SPSS file which has the data sheet for discriminant analysis. I will quickly explain the data sheet, and then we will see how to we'll see the steps how to run the discriminant analysis in the SPSS. So we'll just open SPSS. So the file name is discriminant analysis dataset. So you need to open that file. So this is a small data set. So here there is a product. That product has got 4 criteria on which the buyer would decide whether to buy that product at that quality level or not to buy. So a set of buyers were given the product, and based on that they have been asked to give a rating on the 4 criteria. Here they mentioned durability, lightweight, low investment, rot resistance. So on a 11-point scale, they had been asked to give the rating, 0 being the worst and then 11 being the highest score. So here they have given the scores, and also they have mentioned whether they will buy it, or at that point whether they will not buy it. So with this score, what we are trying to do is we are trying to the buyer and non-buyer, that is the categorical variable, the dependent variable, and then we have the 4 independent variable, which is the durability, lightweight, low investment, rot resistance. So with which this is the data which is currently available, with which we are trying to create a discriminant model. With that model, for any future values of rating of that particular product, we could decide whether will somebody buy it or whether they are not going to buy it. So that's how that's the data set. So we'll see. So here the buyer, non-buyer, the first column is the categorical variable, which is the dependent variable. In the first session, I did not mention this. Is my SPSS sheet visible?
Yes, sir, it's visible.
Yes, sir.
Yes, sir.
Okay. So here yesterday I forgot to tell you this. In the variable view, in the variable view, if you see, the first one is a nominal one, categorical variable, and all the other 4 variables are scale variable. Whenever you have categorical variable, we'll have, like, say for example, gender, we'll have male, female. So we'll have some string over there. So SPSS will take only the numerical things. So in that case, we need to code the data, and then we need to load it into Excel. So the coding is, we can do it under the values column here in the variable view, where if you click on that, you will get a small button there with 3 dots. When you click, you can give the value. Say, for example, 1 for male. So 1 could be the value, label could be male. 2 for value, and label could be female. And then you need to add it to this particular box. So here I have added 0 as non-buyer. So I have coded it like this: 0 as non-buyer and 1 as buyer. So 2 categories we have. So coding, already I have done it. You don't have to do it again. Okay. So now we'll go to analyze menu. Go to analyze menu. So I told you discriminant analysis is one of the classification techniques. So you need to go to classify. Go to analyze menu and go to the option classify. And then you will get a sub menu. In the sub menu, there are different methods available. So here we are going to select the option discriminant. So we have to select the option discriminant. So analyze menu, classify, and then discriminant. When you click on that, the discriminant analysis dialog box opens. On the left side compartment, you will have all the variables. So here, first is the grouping variable, which is the categorical variable. So click on the left-hand side and click on the arrow mark so that it comes to the right-hand side. And the moment you put it to the right-hand side, you could see that next to the variable, you'll have 2 question marks over there. So next to that, there is a button which says define range. So we have to give the minimum and maximum value. Click on that define range. So here the minimum is 0. 0 stands for non-buyer, and 1 is the highest value, which stands for the buyer. So give us continue. So in this case, the maximum is 1. So this we need to give, the range has to be defined. After that, we need to give the independent variable. So we have 4 independent variables. So click on the first, left click on the first one, press your shift button on the keyboard, hold it down, press the shift button on the keyboard, hold it down, and click on the last item so that the entire item will be selected. Click on the first item, hold the shift button down on the keyboard, click on the last item. This will select the entire list of items. And then before the independent box, there's a small arrow, click on that so that all the 4 variables will be loaded into the independent box. So now we have loaded the variables, categorical variable and also the independent variable, which is the scale variables. Now here, click on the statistics button. So statistics button, what are the things we have to select here is you click on means, under descriptives shelf, and then you click on box M, and then under function coefficient, you click on unstandardized. And then matrices you select within groups correlation. So 4 things we are selecting under descriptives, means and box M's. And then under function coefficient, we are selecting unstandardized. Under matrices, we are selecting within group. Okay, and then continue, click on continue. And then click on classify, click on classify. So here, the default settings are there. It says all groups equal and also within groups. So we are not going to touch anything over here. You can just leave it to the default settings over here. Click continue. Save option, click on save option. And then the first checkbox, you need to make a tick on that. It says predicted group membership. So finally, the final objective is, the penultimate objective is to classify the items into 2 different groups. So that is the predicted group membership. You need to give a tick mark, and then you click on the continue button. So the save, whenever you have a save option, when you give the save option, what will happen is SPSS will compute something, and then it will save it to the data sheet. It will create a new variable, and it will save that value to the data sheet. So here, what I wanted to compute, what I wanted SPSS to compute and save is, I wanted the SPSS to use the data, available existing data, and to calculate and find out each and every case over there, whether it falls under buyer or non-buyer. So that SPSS has to decide based on the data what we have, based on the function what we derive at, SPSS has to calculate, and it should give me the classification. So that will come as a separate column in the data sheet. So that we are giving that, and then continue. So only 2 items we changed. Under statistics, we selected 4 options: means, box sum, unstandardized, and within groups. And under save option, we gave the first one, predicted group membership, and continue. So now the moment we give OK, SPSS will run the test. So here it has given us the outputs. So here, group statistics is the tape. So here you can see there are 18 items over here in the data sheet. And then the group statistics, you can see now it has categorized non-buyers as a list, buyers as a list. You can see the numbers here. 9 numbers are there in both non-buyer and buyer category. And we have 4 independent variable: durability, lightweight, low investment. It has computed the mean for every independent variable, and it is classified into buyer group and non-buyer group. So you can see the mean for durability is higher for buyer, and for non-buyer it's very low. Lightweight is higher for buyer, and also it is low for the non-buyer. Same as that low investment. Look at the rot resistance; it's almost close, and it is actually for buyer it is less. For the non-buyer it is little bit higher, but the difference is very less. And when you come down to so these are the correlation coefficients, durability between the variables. durability, and lightweight, you could see that has the highest correlation, 0.64, and you have the other correlation also. So here, the independent variables, they should be correlated. That's what, one of the criteria. The independent variables, it should be correlated. But at the same time, between them, the correlation coefficient should not go beyond 0.75. If it is very highly correlated, then we might have some problem. We might have multicollinearity problem. So if in case any of the two variables are very highly correlated, so probably we have to drop one of the variable and then rerun the discriminant analysis. So that's why we computed this correlation matrix. So here you need to understand the correlation coefficient should be less than 0.75. So in our case, all the correlation coefficient less than 0.75. So it's fine. We can go ahead with this. Then we have box test of equality of covariance. Now here in this table, you could see there are two categories as we have non-Bayer and Bayer. So here what we say is, in the categorical variable, dependent variable, we have two categories, Bayer category, non-Bayer category. And these two should be at the extremes. They should be totally different. They should not be closer to each other. Their values should not be closer to each other because they are opposites. We are trying to differentiate them. So they should not have any correlation. They should be totally apart from each other. So there should not be any covariance between the categories in the dependent variable. So for that, we are testing this. We use the box test. Box test has given a test here, and the significance score is 0.310. Generally, what do we do when the significance score p-value is less than 0.05? We reject the null hypothesis. In this case, what we are testing the covariance between the two categories here. So how would be the null hypothesis form? Null hypothesis, there is no significant covariance between the groups. So that's how we phrase the null hypothesis. There is no covariance between the group. So here the significance is above 0.05. So we are going to accept the null hypothesis. In this discriminant analysis, for this case, accepting the null hypothesis is good for us. P-value should be greater than 0.05, because when you accept the null hypothesis, what are we accepting? We are accepting the fact that the two variables are not covariant. So that's what we are concluding. That's what the condition we want. The categories which we wanted to differentiate or discriminate should not co-vary. That's the thing we want. So that's why in this case, significant value should be greater than 0.05. In other cases, whenever we do any other test, correlation test or regression or ANOVA or chi-square, we generally say the significant value should be less than 0.05. In this case, significant value greater than 0.05 is desired, because we want these two variables not to co-vary, among themselves. So that condition we need to check. If this is not there, then there is no point in using discriminant analysis. So remember this, it has to be greater than 0.05. And then before we go to this summary of canonical discriminant function, let us just quickly see the objectives of the discriminant analysis. The first objective, we said that we need to develop the discriminant function. The discriminant function looks like this: b is equal to b0 plus b1 plus x1 plus b2 plus x2. So this function we need to arrive at. So from where we can arrive, get all those data is, if you scroll down to canonical discriminant function coefficient, this table, canonical discriminant function coefficient. So in this table, they have given some values for durability, the lightweight, low investment, rot resistance, and also there is a constant. Now this constant value is our b naught in the discriminant function over here. The constant value in that table is what is the b naught, and the values they were given against our independent variables, 0.621 minus 0.57. All those variables are the b's, the discriminant coefficient. So now b naught we have, B1 can be taken from the table. X1, X2, X3 are our own independent variables. So once we frame this equation, for any known values of X1, X2, and X3, the D, which is the discriminant score, can be computed. Once we set this mathematical equation, for any known values of our independent variable, which is X1, X2, X3, X4, in this case, it is the durability, the low investment rot resistance, and all those 4 independent variables. For any value of those 4 independent variables, we could calculate the discriminant score, because the unknown things are the B0 to B1, B2, B3. All those things we have it, we could take it from this particular table. So with this, we can write the equation. So in this case, how do we write it? We'll write minus 1.802 plus we need to multiply minus 0.157 into x1 plus minus 0.191 into x2 plus minus 0.57 into x3 plus 0.621 into x4. So like that, we need to write the discriminant function. So I think, sorry, I reversed it. Durability is our first factor. So it is 0.621 into x1, and then it goes minus 0.57 into x2. It goes off like that. So this is how we form the discriminant function. This model we need to create. So that is our first objective. Second objective was examination of the significant difference among the groups. Significant difference among the groups. Here the groups are what? Buyer and non-buyer. How did we examine the difference among the group, whether it is significant or not? We did it with the help of the box test. Box test confirmed that the both groups are totally they don't co-vary, they are different. That we concluded. Third one, determination of the independent variable that contributes the most for the intergroup discrimination. So here we have 4 independent variable. So we need to find out which is the most which is impacting the which is discriminating the dependent variable the most. So in order before we find that, we need to check whether the model which we created, whether that model is acceptable or not. So for that, we have 2 things. One is the Wilks lambda. The Wilks lambda, there is a significance value over here. The significance value, it says 0.04, which is less than 0.05. In this case, it should be less than 0.05. If it is less than 0.05, our model is okay. We can continue with the model. Number 1. Number 2, in the eigenvalue table, we need to look at the canonical correlation. Number 1, eigenvalue should be above more than 1. If it is higher than 1, if it is more much higher, it's good for us. Second thing is, the important thing is canonical correlation, which we need to compute. So the canonical correlation here, it has come as 0.713. Now this is similar to the R-square value in the regression analysis. So I'll tell you how. So we need to calculate the square of this value. It's like R value. So we need to compute the square of this. So it is 0.713. So we need to compute the square of that. So let us see what the value comes. So 0.713 multiplied by 0.713. So this is 0.5083. So 50.83. So what can we interpret from this is, we can say that the model what we have developed is able to explain that the difference up to 50%. The balance almost 51%. The balance is not explained by this model. Somebody, whether they will buy or not buy, is explained by these 4 independent variables only up to 50% only. The balance could be based on some other reason which we have not taken into the study. The balance 49% could be because of some other reason which we have not taken it in our study. We have taken only 4 independent variables. So 0.5 is okay. That's what our model says. So that is, we need to interpret this also. When you interpret discriminant analysis, we need to interpret this, because this will convey to what extent we are able to explain the dependent variable. So this we need to interpret. Now we need to go to the third objective, which says which independent variable is impacting the discriminating the dependent variable most. So in this table, you come down to structure matrix. We have 2 tables here: standardized canonical discriminant function and structure matrix. So in the both the tables, you have the coefficient values over there, and this coefficient value should be higher. Whichever independent variable has got the highest coefficient value, that is the independent variable which is very important to discrimination. For differentiating, the more weightage, the more important variable is, in this case, it is durability, because the coefficient is 1.225. Even the structure matrix, the coefficient is very high for the for durability. So we could say that durability is the most important factor to group a case, whether to put it in Bayer category or non-Bayer category, so that we can identify. So that we have identified. Then fourth one, classification of the cases. So each and every case needs to be classified into either of the two groups. So that option already we clicked when we ran the test. So you go to the data sheet, go to the data editor window. Now you will observe in the data editor window, there's a new column which has been created. If you go to the variable view, you could see the new column has got a name, and then it has been stored as a categorical variable. And then if you go to the values also is there. 0 refers to non-Bayer, 1 refers to Bayer. So this column we didn't create. SPSS has computed and saved it over there because we selected that option on the save option. Because of that, this new column has been created. So now here, our discriminant function, what we arrived at, that using that function, SPSS has classified these four values like this. So if you look at this, this is the original, the real classification. This is the predicted classification. Okay, so here you could see up to 9, we have 9 Bayers. Okay, but here one of the Bayer has been wrongly classified as non-Bayer. So always the model which we design will have little bit of inaccuracy. So that is being evident here. We cannot have predicted to 100%, but so here we lack some discrepancy. But it's trustable. We'll see why it is trustable. So here one of the case has been wrongly classified. Same as that, here we have 9 non-Bayers, but you would see here 2 of the non-Bayers has been classified by the function as Bayers. So that is the thing. So here, if we could say that, like, we had 18 numbers. So out of 18, 3 is a mistake. Okay. So out of 18, 3 is a mistake. So let us calculate the percentage. So it means 15 is correct. 15 items cases has been correctly classified. So 15 by 18 into 100. So 83% is the accuracy. So with this, we could go and do the discrimination for a real data set with our model. Or if in case you find it less, if you want this to increase it to 90, then probably you might require more variables, additional variables to be included. And then you need to collect data, you have to rerun it and see whether it can go beyond 90. And then you could conclude the model. Okay, so that's all about the discriminant analysis. So now we'll move on to the next one, factor analysis. So factor analysis is a technique that is used to reduce a large number of variables into fewer number of factors. Whenever we do research, we'll have a list of variables. Lesser the number of variables, easier it will be for modeling and things like that. So it's a good practice to do a reduction, follow a reduction technique and reduce the number of variables into a fewer number of factors. So that's what the factor analysis does. Mostly it is used in exploratory research. The goal of a factor analysis is to reduce the number of variables. When I say exploratory research, in the initial stages, when the sufficient theory is not there for your problem area, so at that time you do not even know what are the different factors which is going to impact the dependent variable. In such a scenario, we could go for the exploratory factor analysis. So it will help us to find out the factors and we could give a suitable name for it. So there are certain preconditions for factor analysis. I have listed it, some of the main preconditions. One is the variables need to be continuous. It should be on the scale. It should be a scale variable. Um, whatever variables you use, it should be scale variable. Second, the size of the sample needs to be at least 4 or 5 times the initial set of variables. Suppose you have 20 variables in your measuring instrument in your scale. So if you have 20 variables, 20 statements, your sample size should be at least above 100. Only then the factor analysis would be effective. The initial variables need to be correlated. The variables, whatever you have, they should have correlation between them. They, because they are measuring a particular concept, so the variable should have sufficient correlation between them. And then there is a statistics we'll be using, KMO, Kaiser-Meyer, coefficient. We'll be using the test. When I run it, you will understand. So this KMO value should be at least above 0.5. If it is less than 0.5, the sample what we have taken, the data what we have is not suitable to run factor analysis. So probably we might get additional samples and then again run KMO test, and then you have to find out whether it is above 0.5. If it is less than 0.5, we cannot run factor analysis. We cannot the interpretation will not be justifiable. So this is the first step. Like, we will have a KMO table where the KMO value is above 0.5 only, we'll proceed with factor analysis. So these are the preconditions. So in a, say for example, I put up a list over here. So in your research, say for example, there are 9 variables. In your questionnaire, you have 9 questions. So those will be the 9 variables. These 9 variables, say for example, variable 1, 2, 3 are highly correlated to each other. Variable 4, 5, 6 are correlated to each other. Variable 7, 8, 9 are correlated to each other. So these 3 variables have some commonality, which will with which it predicts a factor which is actually not visible. It's not on our questionnaire. Questionnaire has got only 9 variables. This factor is unobserved, but because these 3 variables are having a commonality between them, we could replace these 3 variables with a unobserved factor. The 3 variables indirectly predict a unobserved factor. So factor analysis, what it does is it reduces the number of variables into a limited number of factor. For example, so this was the rater model on service quality developed by Parsuram in the 1980s. So at that time, there was not much theory on service quality. So they did a huge research in the banking industry, and then they arrived at they had a big questionnaire with a huge number of variables, and after testing, they reduced the variables to 24, and they had identified 5 underlying factors, and those factors they named it as reliability, responsiveness, assurance, empathy, and tangibles. So the factor analysis also helps us to reduce these variables into a limited number of factors. So the variables are known to us, which are observed, which are measured. The factors are underlying, which is not known to us. They are also called as dimensions or constructs or latent variables in different, they use different names. Okay, these are basics. We all know this. Important thing which we need to notice, every factor at least should have 3 variables. If the variables are less than 3, that's not nice. That will not be good for factor analysis. If it is more, it is good. If it is less than 3, we need to think about it. For a factor to be efficient, if it is more than 3 variables, it's good. When we speak about factor analysis, we generally speak about exploratory factor analysis and confirmatory factor analysis. So exploratory factor analysis, as I said, at the initial stages of your research, we might be doing the exploratory factor analysis to identify the different variables and the underlying factors and to reduce the number of variables. Confirmatory factor analysis is confirming the model at the end of the research. Yeah, we cannot use SPSS to do CFA, confirmatory factor analysis. But we have IBM has another kind of a plugin or add-in software called as AMOS. AMOS, if you can purchase it, if you can install it, that could work well along with SPSS, and you could also run CFA in SPSS itself. If you don't have AMOS, we cannot run CFA. So in this thing also, we are going to see only the EFA, exploratory factor analysis. So there are 2 major steps in EFA, exploratory factor analysis. One is factor extraction, another one is factor rotation. So factor extraction would determine how many number of underlying factors. And once you have determined the number of factors, and then factor rotation will give us the individual variables along with the factor loadings that could be grouped under the different factors. So when we run it, we'll see. And the factor extraction, there are different techniques available. SPSS gives us various options, but the most common one is the principal component analysis, which will give us how many factors are there in our data sample. So we'll be going with the principal component analysis. And also the rotation technique, we had SPSS offers different rotation technique as well, but the most commonly used is the Varimax rotation, because it provides much of the variability between the factors. So Varimax rotation is generally preferred. We will also go with the Varimax rotation only. So now you open the now you open the factor analysis dataset. So there is another dataset which says factor analysis. So open the factor analysis dataset. So here, go to the variable view. So we'll just have a look at the variable view. So here we have the SSN number, the gender is there, overall satisfaction is there, and then we have 20 different variables. 20 different variables. The last variable you need to change it to scale. It's mentioned as nominal. Change it to scale. Okay. So all the 20 variables should be on the scale variable, and we need to reduce this 20 variables into number of factors. So we need to identify how many number of factors, and then we need to group these variables into those 4 factors, the way I showed it in the rater model. So go to analyze. So we'll start doing the factor analysis. I hope you opened the factor analysis datasheet. Go to analyze. In the analyze menu, there is an option which says dimension reduction. So go to dimension reduction. In the sub menu, the first option says factor. So we have to select that option, which is for factor analysis. So analyze, dimension reduction, and then factor. Click on the factor. The factor analysis dialog box opens. So in that, we know the variables to be selected. The first 3 variables are not part of our study. So we are going to take from the 4th variable. Left click on the 4th variable. Hold the shift button on your keyboard, and then click on the last variable. That would select all the variables from 1 through 20. Select all the 20 variables. And to the right hand side compartment, there is a compartment named variables. Before that, there is an arrow. Click on that arrow so that all the variables are moved to the right side compartment. So now we have brought the ingredients into the system, and then go to the options, descriptives, go to the descriptives button, click on the descriptives button. So here you need to select on in the correlation matrix, select coefficient, significance level, the last one, KMO and Bartlett's test of sparsity. So 3 things you need to select in the correlation matrix: coefficient, significance level, and KMO and Bartlett's test of sparsity. So 3 things we have to select. Continue. Click on extraction. Click on extraction. The extraction method here is the principal component extraction. So if you click on that, you will see there are so many methods available. So we'll go with as I said, we'll go with the commonly used one, principal component analysis. And in the analyze, let it be there, correlation matrix. Display, you click on the scree plot also. Scree plot is a visual way of finding out how many factors. So scree plot will give us a chart or graph. With that, we'll be able to find out how many factors are there. Eigenvalue greater than 1, and then click on continue. Click on continue. Then go to rotation. Go to rotation. Rotation, as I said, there are multiple options. We'll select Varimax rotation. We'll select Varimax rotation and continue. And continue. And then scores, we are not going to do anything. Click on options. Click on options. In the options, under coefficient display format, and this is just a formatting option. Under the display format, click on the first one, sorted by size, and then suppress small coefficients. So 2 things we are selecting: sorted by size, suppress small coefficients. Generally, we ignore if the coefficient value is less than 0.3. So correlation above plus 0.3, considered moderate correlation. So we'll keep 0.3. So we select two things, sorted by size, suppress small coefficient and give the value 0.3 and then continue. 0.3, don't forget the decimal point. And then we are ready to run the factor analysis. Click on OK. Click on OK. So this will give us the factor analysis. The first table is the correlation matrix. In the correlation matrix, as I told you, we had 20 variables. All the 20 variables should show some kind of a correlation. So for that only we have this table, but because we have 20, so many variables, 20 on the x-axis means rows and 20 on the columns, it will be very difficult to have a look at everything. So what we could do is we could just scroll down, directly go to the KMO Bartlett's test. So here the KMO measure of sampling adequacy is 0.712. The threshold benchmark is, it should be greater than 0.5. So in our case, it is more than 0.5, it is 0.7. So we could go ahead with factor analysis. Bartlett's test of sphericity, it gives us whether it tells us whether the variables are correlated significantly. So here the significance is less than 0.05. So we could say that the variables are significantly correlated. So we could well go ahead with the factor analysis. We don't have to look at the communalities. This table is very important, the total variance explained. So in the total variance explained, you could see here, we said that we mentioned that eigenvalue should be greater than 1. So it has selected the first 4 factors here. The first column says component. So component 1, 2, 3, 4. So we have 4. We may have 4 underlying factors, and eigenvalue after that is less than 1. So we are ignoring that. And then the total variance explained, the cumulative percentage of variance explained is for 4 factors is 52.10. It means only 52 generally this should, we prefer it should be above 60. So in this case we have got 52%. It means the total variance explained by these 4 factors is only 52%. If in case you go for the 5th factor, it could explain more, but as per our eigenvalue calculations is it should be greater than 1. So we are restricting to 4 factors. Our idea itself is dimension reduction. Our idea is to have efficient and adequate number of factors. So going more is not feasible. And you can also see that if as you move forward also, you will see the more number of factors. We have 20 things. It will take up to 16 factors to get 100% TV explained. So so as per the things, we stick to 4 factors with the TV of 52%. So the scree plot also suggests that. So in the scree plot, how do we interpret this? I'll just show you. I'll just copy this to a Word file, and then I'll show you how to interpret the scree plot. So here, the scree plot has plotted the eigenvalues against the component number. We have 16 factors. So the eigenvalues have been plotted. So how to interpret this? We have to draw a straight line starting from the first one. So I'm going to draw a straight line from here, from this point, where the eigenvalue is, the highest one. So from there, I'm trying to draw a straight line in such a way that I connect the points here. Okay, I connect the points here. So here, you could see the line actually bends like a L bend. So I just drawn a straight line. Yeah, so I just drawn a straight line. You could see these 4 points fall exactly on the straight line, but the 5th point is not on the straight line, and after that it is becoming a L bend. So here, the scree plot, we have 4 points on the straight line. So number of factors is going to be 4 only. Okay, so now the first step is factor extraction. We said we need to decide how many factors are going to be there in our sample variables. So here we can conclude that there are 4 factors. And then component matrix will give us the factor loadings for individual variables. So with these variables, we need to group it under all these 4 factors. So which variable is correlating more with which component? That's what this matrix will tell us. And you could see here, the first variable is loading on the first factor, and it is also loading on the third factor. So it's very difficult to interpret this. So because of this, we go for the rotated component matrix. We said varimax rotation, right? So we go for the rotated component matrix, where if you also remember, we selected, we need to sort it, and value should be above 0.3. So now SPSS beautifully categorizes the variables factor wise, and it sorts it in a ascending order based on the factor loading. So this way, out of the 20 variables, we could say these 5 variables load under factor 1, the next 4 variables load under factor 2, the next 4 variables load under factor 3, and the last 3 variables load under factor 4. So we have got the factor extraction, we have 4 numbers, and then we have got the groupings also, individual variables, which variables are loading under which factor is also identified. Now the researcher, what they do is, looking at the variables, they give a suitable name for each and every factor. The way in which Parasuram has given for the rater model. So they group the variables, and then they have given the suitable name for it, like reliability, responsiveness. Like that, we have to give a name for the 4 factors that we have identified. So in this case, we could give the names as clarity, decency, helpfulness, and reliability. So that's all about factor analysis. So now we move to the next one, cluster analysis. Cluster analysis is a classification technique. In discriminant analysis, we had a dependent variable. We had a dependent variable which needs to be classified. Okay, so cluster analysis is not like that. Cluster analysis is, we have a sample data. Among the data, we look for similar variables. We group it under different clusters. Primarily used for segmentation studies in market research, when you want to segment your customers based on some variables. So for those things, we use the cluster analysis. So it's an exploratory data analysis tool for organizing observed data into meaningful clusters based on combination of variables. So here on the left hand side, you can see the data which I have plotted, which is unclustered. But when I classify it based on some criteria, you could see based on that criteria, the lower part is in red color, means those dots has some similarity. The items which are grouped under blue has some similarity. The items which are marked as green has some similarity. So within the cluster, they are very homogeneous. Between the cluster, they are heterogeneous. So the homogeneous items are grouped together as clusters. So if you want to do a customer segmentation based on some their behavioral traits, or based on some aspects of the customer purchasing behavior, then the clustering technique is very useful. And we could individually group these customers, which customer is under which cluster, and we could then further target our promotional activities or promotional messages. We could give them some targeted offer. We could run some targeted campaigns for the cluster specific customers. So for that, we use the clustering technique. In SPSS, we have 3 types of clustering: hierarchical, k-means, and two-step cluster. We are going to see hierarchical and k-means cluster in this session. In hierarchical cluster, what it does is, in this technique, initially each data point is considered as an individual cluster. So clustering is very simple. Say, for example, you go to a classroom, the students are there, and I ask you to group the students based on the similarities in their height. So what you will do, you'll take 6 feet and above, you will group it separately. 5 feet and above, you might group it separately. So based on some criteria, we are classifying them. That's what is cluster analysis. So in hierarchical clustering, what we are doing is, we are taking one individual one data point, and we'll put it in, say, cluster 1. We'll take another data point, compare it with them. If it is similar, we'll put it in that cluster. If it is not, we'll put it as a separate cluster. So like that, every data point is compared and grouped. We call this the iteration. So many number of times it is run, and then it will group them into different clusters. Either at the end we'll have either one cluster, or we may have k number of clusters. We use the alphabet k. So here I have a flower. This is iris flower. So this iris flower has got three types. So iris setosa, iris versicolor, and iris virginica. So how do they differentiate these flowers is based on their sepal and petal length and breadth, based on which these flowers could be differentiated, whether it is iris setosa or versicolor, iris virginica. So I have a data sheet. So I have a data sheet, which is there in the link. You could download that one and open it. So that has the petal and sepal length for the flowers, with which we are going to cluster the, we are going to segregate or classify the flowers into clusters. Okay, so that is the hierarchical cluster. K-means cluster does the same clustering only, but we will have a knowledge of how many clusters are there in the group. Suppose if you have the knowledge that it has got 5 clusters, then we could run k-means clustering, where we'll say that there are 5 clusters. So we'll ask the computer, we'll ask the SPSS to classify the data into 5 clusters, or say 3 clusters. We'll give the number of clusters. In hierarchical clustering, we do not know how many clusters are there. We are asking the SPSS to compute and tell us how many clusters are there. In k-means clustering, we will tell how the system to group it in k number of clusters. So generally what they do is they generally run the hierarchical cluster, find out how many clusters are there. Then we'll use k-means cluster to individually classify each and every item, each and every data point into those many clusters. So that's what we'll do. So we'll run both hierarchical and k-means clustering. So we'll open the third file, clustering dataset. We'll open the third file, clustering dataset. We'll open the third file, clustering dataset. So here you could see column 1, column 2, column 3, column 4. We do not know which is petal length, which is sepal length, which is sepal breadth and petal breadth. But something is there. Just for our understanding, I have also given the classification. We'll see how accurately the system will classify. Okay, this is the original classification. We will see how the system will classify this. So same way, if you go to the variable view, you could have all the things are in scale, and the classification is in the categorical variable. Okay, so go to this one, analyze. Go to analyze, classify. In classify, so we are going to use hierarchical clustering. So go to analyze, classify, hierarchical cluster. In the hierarchical cluster, we are going to cluster it based on these 4 variables: column 1, column 2, column 3, column 4. So select all column 1 to 4, and then move it to the right side compartment. Move it to the right side compartment. Go to statistics. This agglomeration schedule is very important. So that is by default it is selected. Leave it. And then plots we don't want. Click on method. In the method, we are going to use, there are so many methods. We are going to use the Watts method, which is commonly used. Interval, it should be squared Euclidean distance. Let it be there. And so these 2 things we should ensure. Cluster method is Watts method. Interval is squared Euclidean distance method. Give on continue. Give on continue. And then click on OK. So 2 things: statistics, default option, agglomeration schedule, method, Watts method, and interval, squared Euclidean distance, and click on OK. Click on OK. So this will tell you there are 150 data points here, and then you have this table agglomeration schedule. Over there you have the stage. The first column, it says stage. So we have 150 cases, and then if you scroll down, there are 149 stages. So now the clustering has been run by the system, and this schedule is prepared by the system. So we have 150 cases, but we get 149 stages. So this table is important. Here we need to look at the coefficient, the 4th column. Sorry. Yeah, in the agglomeration schedule, the 4th column, it says coefficient. First column is stage, the 4th column is coefficient. So we have to look at the corresponding coefficients for these stages. Okay, so here how to interpret this: if you scroll down, if you see that coefficient keeps on increasing from a decimal point to it keeps on increasing. Finally, for the 149th iteration, the 149th stage, we have got a coefficient of 680. So from this point, we have to look back and we need to find out where there is an abrupt change. Okay, where there is an abrupt change. So you could see here from 680 it has gone to 155. From 155 it has gone to 79. From 79 it has got to 58, a single digit number. It's only from 79 to 58. So then the difference is substantially reduced between this. So manually you could calculate this, or you could also I can also show it with a plot. So I'll take Excel for quickly generating the plot. You could plot it and see where you get a change, like a scree plot. And then you don't have to do this, just have a look at it. I'll just quickly make a plot just for the interpretation's sake. So I'm just copying the stages and the coefficient to the Excel sheet. And then I don't want to plot everything because it will be too many data. So we have 149, so I'll plot up to 130. So I'm going to insert a scattered plot, a line chart. So here you could see the 149th iteration. From there it has reduced. It has reduced. From 147, if you see, it is becoming like a horizontal line. Before that, there was a slope was there, but after that, it is becoming like a horizontal line. So 147 is the point which you need to note down. So we had total number of cases, we had 150, and 147th stage, it is becoming a horizontal line, means the difference is drastic. So the difference between these two, 150 minus 147, which is 3. So 3 is the number of clusters over here. So this is how you interpret the agglomeration schedule. So this is how we decide on the clusters. So in this case, we have identified 3 clusters. Okay, we have identified 3 clusters. And then what we are going to do is we are going to run the k-means clustering, and we will ask the system to group these items into the 3 clusters. So we'll go to analyze, go to classify, and select k-means cluster, move the 4 variables, column 1, column 2, column 3, column 4 to the right. And then if you come down, number of clusters default is 3. We need 3 clusters, make the number as 3. Iteration, let it be there. Go to the save option, and then the save option, you select cluster membership. Now this will create a new variable. Always save option will create a new variable. And it is system is going to tell us which data point should be grouped under cluster 1, which data point should be grouped under cluster 2, cluster 3, like that it is going to tell us. So give the save option and give the cluster membership. And yeah, here ANOVA table could be used for interpretation. We'll select ANOVA table, and then in the options, we'll select ANOVA table, continue, and then click OK. So now this has run, k-means clustering has done. And then here, if you just scroll down to, so you can see here, it is grouped into 3 clusters. You can just come down to ANOVA table. You could see here the significance for all the 4 cluster, all the 3, the 4 variables are significant. Means these clusters are significantly different. And if you come to the last table, which says number of cases, cluster 1 has got 38 numbers, cluster 2 has got 50 numbers, cluster 3 has got 62 numbers, total 150. So if you go to the variable view, the data editor window, if you go to the variable view, data view, now you could see there's a new column that has been created, and you will see it has been grouped into different clusters. The first data point is grouped into 2, second data point has been like that, 3, and cluster 1, like that it has been grouped. So whether it has been grouped correctly or not, we'll just have a look at it. So I'll just quickly run a frequency. We'll see whether it has the actual. These are the actuals. Column 5 is the actuals. These are the predicted values. We'll see whether the prediction is correct. So we'll quickly run a frequency for column 5 and the new column. And here you would see for the column 5, you will see 3 flowers are 50, 50, 50, total 150. So we had 50 numbers of each variant, but in the clustering, the system has clustered. The second flower, it has clustered 50 numbers, but the first flower only 30 has been grouped here. The third cluster only 62 has been grouped here. So this is what the prediction looks like. So now there's a bit of inaccuracy. So we need to have a look at it. We need to again maybe collect more data, rerun the algorithm again, and see only when you feel that the accuracy is good, then you could use it for a live data. When the live data comes, you could run this algorithm and you can check and you could group it into these variables. Many times the names are not available. The SPSS will give you cluster 1, cluster 2, cluster 3 only. So it's the user who has to give a name, suitable name to it and group it. And if in case future, if the live data, if that data follows a similar pattern, then we could easily classify into the named clusters. So that's what I have for the day. So we have discussed discriminant analysis, we have discussed factor analysis, and we also discussed clustering technique. So thank you so much. Any doubts?